If you walk into a major industrial facility, think a massive water treatment plant, maybe a high-volume manufacturing floor, or even a big data center, you'll be surrounded by this quiet hum of power.
Mm.
But what you're really hearing is control. We're talking about managing hundreds, sometimes, thousands of individual motors all at once, from these giant pumps to tiny little conveyor belts.
All running in concert.
Exactly.
Yeah.
And today we are opening up those towering metal cabinets that serve as the centralized brain for all that motion,
Yeah.
the Motor Control Center, or MCC. We've got a dense stack of standards, engineering specs, and some critical safety guides.
A lot to get through.
A lot. Our mission here is to strip away that intimidating facade and really understand exactly how these industrial workhorses are built, how they're protected, and why a specific choice made maybe decades ago might determine the safety gear you have to wear today.
It's a great place to start. And, we should be clear. When engineers talk about an MCC, they're referring to a very specific piece of equipment defined by NEMA and UL standards.
Right.
It's a floor-mounted assembly of these enclosed vertical sections. And they're all unified by a really critical component, the common horizontal power bus. And crucially, it principally contains what we call combination motor control units.
Okay, let's unpack that definition, because it tells us immediately why MCCs just dominate heavy industry. I mean, why consolidate all this control into one place instead of having disparate components just scattered near every motor?
It really boils down to efficiency and scalability. When you centralize, you dramatically speed up installation and you simplify all the wiring management.
I can imagine.
Instead of running heavy control wires all over a massive building, you run power to one central point. And for facilities that grow or change processes, it's just so much easier to modify.
So it's future-proof in a way.
Exactly. You can add a new vertical section or swap out a starter unit for a bigger horsepower application without tearing up half the building's infrastructure.
Yeah.
It's literally built for expansion.
Okay, so let's get inside one of these units.
To understand the MCC, you have to understand the fundamental unit it contains, the combination starter. When you open one of those compartment doors, that plug-in enclosure is doing three things all at once.
Three things. Okay.
It's providing the actual motor starter, the short circuit protection, that's either fuses or a circuit breaker, and a disconnecting switch that allows you to safely isolate the unit from the main bus power.
So we've plugged in this combination starter. What are the two core devices inside the actual motor control part? What does each one do?
Right. At the heart of it, you have the contactor. That's the remote switch that turns the motor on and off, getting signals from a PLC or some control circuit.
Okay.
But the true protector, the real bodyguard for the motor windings themselves, is the second component, the overload relay.
And the distinction here is key, right? We're not talking about a massive short circuit yet. The overload relay is handling situations where the motor just draws too much current over time, typically because it's struggling. Precisely. If that conveyor belt gets jammed or a pump starts seizing up, the motor works harder, it pulls excess amps, and it heats up. And that heat is what kills the insulation. The overload relay detects that sustained excessive current before the motor is permanently damaged.
I always find those older methods of protection just fascinating. We're talking about components that are designed to fail, or at least trip in a controlled manner based purely on thermodynamics.
They are elegant, if a bit slow. Think about the traditional thermal mechanisms. You had the bimetallic strip that's two different metals welded together. When they're heated by the motor current, they expand at different rates.
And it bends.
It bends, and that physically opens the control circuit contacts. Or you have the melting solder pot, where a calibrated alloy melts at a specific temperature, releasing a mechanism that trips the starter.
Ah, the old solder pot. That sounds incredibly reliable, like a dedicated thermal fuse, essentially. But I bet facility managers spent half their downtime just waiting for those things to cool down enough before they could even try to reset them.
That was the crucial limitation, the mandatory cool-down period dictated by physics. Fortunately, modern MCCs use solid-state electronic technology, and they offer a level of protection the old thermal units just couldn't touch.
How so?
Well, a good example is a solid-state starter like the ESP100. It measures the current electronically, which means you get faster, more accurate tripping on overloads. But its real advantage is complex protection.
Like what?
Like monitoring for phase loss. If the starter loses one of the three incoming power supply phases, which can destroy a three-phase motor very quickly, the solid-state unit will trip the circuit, often within 3 seconds, and prevent a catastrophic failure.
Wow. that transition from relying on metals bending to microprocessors monitoring waveforms, that is a massive leap forward in murder life expectancy. And for the designers out there, we should probably touch on scale. That performance level is tied directly back to the NEMA size ratings.
Absolutely. The NEMA size 1, size 2, size 3, it's essentially a capacity rating. It's based on the maximum horsepower the starter can safely handle at various voltages.
So it's a shorthand.
It is. Knowing a NEMA size 3 controller can handle 50 horsepower at 460 volts immediately dictates what that MCC compartment is capable of. It standardizes the entire industrial ecosystem.
Okay. So we've talked about protecting the motor itself with the overload relay. But what if we get a huge short circuit? Not just a jammed conveyor, but a true fault. That relay won't cut it. What protects the rest of the facility and that massive horizontal power bus we mentioned?
Now we're moving to branch circuit protection, and we have to clearly distinguish between an overload and a short circuit.
Two different animals.
Totally different. An overload is excessive current that builds heat slowly. A short circuit is instantaneous and catastrophic. Two conductors touch, resistance drops to near zero, and the current instantly skyrockets. We're talking thousands or tens of thousands of amps.
And this instantaneous event is where the great industrial debate lives. Fuses versus circuit breakers. How fundamentally different are the methods they use to handle that immense spike?
They're fundamentally different in both mechanism and speed. Fuses are, well, they're sacrificial. They operate by having a calibrated metal element designed to vaporize or melt when the current exceeds its rating.
A one-shot device.
A one-shot device. And crucially, current-limiting fuses act incredibly fast. They can clear a fault in as little as 0.004 seconds. That's before the current E even reaches its peak potential during the fault cycle.
And breakers.
Circuit breakers, conversely, are mechanical. They use sensors, thermal or magnetic, to detect the overcurrent, which then triggers a mechanical contact separation. While they are reliable and resettable, they require time for that mechanical movement, often clearing the fault significantly slower than a high-speed fuse.
That millisecond difference in clearing time, that translates directly to the most critical safety issue in any electrical facility: arc flash protection.
This is the #1 differentiator, and it is absolutely non-negotiable from a safety perspective. When a short circuit happens, that delayed clearing of a standard breaker can allow a massive, dangerous arc flash to occur.
And the data backs this up.
It does. Studies by IE and others have confirmed that current-limiting fuses can reduce the arc flash incident energy by up to 90% compared to standard breakers installed in the same environment.
That is a huge number. Can you put that into relatable terms for the listener? What does a 90% reduction actually mean for the person working on that MCC?
It means the difference between mandatory safety gear categories. A fast-acting fuse often clears the fault so rapidly that it suppresses the energy below 1.2 calories per square centimeter.
Okay, and that level.
At that level, standard arc-rated closing is often sufficient. However, if a standard breaker clears the fault more slowly, the energy release can jump dramatically, potentially requiring a full Category 4 suit and gear rated up to 40 calories per square centimeter. That milliseconds difference dictates the required PPE for every maintenance task for the life of that equipment.
That really drives home the safety argument. But let's look at the financial paradox, the total cost of ownership, or TCO. Upfront, the fuses are cheaper, right? Sometimes 20 to 40% less. But replacing a blown fuse means downtime, say, 30 to 45 minutes versus maybe 5 minutes to just flip a breaker handle.
And that's the classic short-term versus long-term debate. A high-throughput facility absolutely hates that 45 minutes of downtime.
Of course.
However, the life cycle costs of the breaker system can catch up quickly. NFPA 70B mandates that breaker systems often require complex testing and calibration every 3 to 5 years to ensure they still meet their tripping curves. That's an expensive, dedicated maintenance project.
And you have to factor in the PPE.
You do. When you factor in the significantly higher cost and logistics of providing that high-category arc flash PPE for all personnel servicing the higher-risk breaker system, the TCO can actually swing back to favor the fuse system, despite the replacement cost. It forces a tough choice between immediate downtime and long-term safety and compliance costs.
This complexity must be why electrical codes enforce specific rules about protection and coordination.
Absolutely. NEC Article 43094 addresses this. It mandates overcurrent protection for the MCC's main power bus. It has to be protected either by a device in a switchboard ahead of the MCC or by a main breaker or fuse section within the MCC itself.
And what about critical systems?
Well, for critical systems like those in healthcare facilities or emergency backups, That's NEC 517.17, strict selective coordination is required.
We've used that term, selective coordination. For those listening who might not work with high voltage every day, why is that so important, especially in a place like a hospital?
Selective coordination is the ability to ensure that when a fault occurs anywhere in the system, only the protective device nearest to the fault trips.
So you isolate the problem.
Exactly. If a motor in the basement has a short circuit, you want only that specific combination starter's fuse or breaker to open. You do not want the main power coming into the whole MCC to trip.
Because if that happens,
You shut down every motor in the facility, potentially including life support systems or critical HVAC. The NEC handbook often favors current-limiting fuses in these applications because their precise, fast operation makes achieving this coordination much more reliable than with standard breakers.
okay, moving beyond just turning on and protecting the motor, modern MCCs are these central hubs for advanced motor management. If a motor needs to start smoothly or change speed continuously, we're looking towards sophisticated drives. What's the defining difference between a soft starter and a variable frequency drive?
They solve two different problems. Soft starters, using SCR or thyristor technology, are designed purely for the startup phase. They slowly ramp up the voltage supplied to the motor over a controlled time, say 5 to 10 seconds.
So it's a gentle start.
A very gentle start. It minimizes the massive inrush current and the torque stress that happens with a direct online start. Once it's ramped up, the motor runs at a fixed constant speed. They're perfect for constant torque loads like large conveyors.
So the soft starter is just about being nice to the motor during acceleration. If you need to actually modulate the speed while the system is running, that's where the VFD comes in.
Exactly. The variable frequency drive, or VFD, or AC drive, regulates both voltage and frequency simultaneously using an inverter section. By varying the frequency, you control the motor's speed throughout its entire operation, not just its startup.
And this is essential for?
For variable torque applications, pumps and fans where slowing down saves immense amounts of energy. For example, reducing a pump speed by just 20% can cut its power consumption by almost 50%.
Wow. Okay, now let's step back and look at the physical structure holding all this sensitive technology. These MCC cabinets have to survive the facility environment. They have to house massive copper buses and contain fault explosions. What regulatory framework governs their physical safety and construction?
It's really a three-way partnership. You have UL, specifically UL 845, which tests the product design for overall safety. Can it contain a fault without exploding?
That seems important.
Very. Then NEMA sets the construction and performance ratings, establishing critical parameters like bus bar temperature rise. If the ambient temperature is 40 degrees Celsius, NEMA standards often limit the temperature rise of the bus to 65 degrees above that.
So keeping those huge copper bars cool is paramount.
It is. And the NEC comes in to mandate safe installation practice, especially regarding physical spacing.
What kind of spacer?
Well, the National Electrical Code ensures safe distances are maintained. For instance, for voltages over 250 V, you must have at least 1 inch of clearance between a live bus bar and any grounded surface. It's all about preventing accidental arcs.
And finally, the MCC construction has to match its environment. A clean indoor warehouse is very different from, say, an outdoor petrochemical facility. The enclosure type is the final piece of that structural puzzle.
It's vital. Enclosure ratings are standardized to protect the internal components. You'll see everything from a Type 1, which is basic indoor protection against a little bit of dirt, all the way up to Type 3R, which is built for outdoor conditions, rain, sleet, and dust.
And even tougher ones for harsh environments.
Oh, yeah. You have the highly sealed units like Type 12, the international IP52 equivalent, designed to keep out circulating dust and corrosive drips. The MCC has to be physically robust enough to survive the facility and the massive fault currents it might see, with bus bracing sometimes rated up to 100,000 amps interrupting capacity.
So what does this all mean then? The Motor Control Center is far more than just a big metal box. It's a highly engineered, standardized ecosystem built on 3 core pillars: centralization for efficiency, component integration via the combination starter, and a robust protection defined by NEMA, UL, and the NEC.
And I think the key takeaway is that when you're dealing with industrial control, performance and safety are just inseparable. Understanding the physical strength of the bus bracing, the environment-specific enclosure, that is just as critical as understanding the sophisticated control logic running inside those units, the VFDs and the solid-state relays.
And this leads us to a final, maybe provocative thought for you to consider. That initial design choice fuses versus circuit breakers, It isn't just a maintenance decision based on a ledger sheet. It's a foundational safety commitment that dictates the exposure level for every maintenance technician for the next 3 decades.
Hmm.
So when facilities undergo safety audits or they upgrade their NFPA 70 compliance protocols, how often are they willing to reevaluate their entire installed protection scheme and invest in systems that fundamentally minimize the daily arc flash risk? That's something for you to explore within your own organization.